So now we start chapter number 1, which is relations and functions. The same chapter you already studied in 11th standard, but now in 12th we have little bit detailed about relations and then functions. So you just recall from 11th standard. Recall from 11th standard what is a relation. So you know relation is a subset of A cross B, where A and B be any two non-empty sets, where A is non-empty set and B is non-empty set. So usually a relation is denoted by capital R. So I'll write here R. Relation R is a subset of a set A cross B. Now again you know that if A and B be two non-empty sets, then A cross B is set of ordered pairs. A cross B is set of ordered pairs, you know. Set of ordered pairs. So R being a subset of A cross B, the relation R is also a set of ordered pairs, which this much we know from 11th standard. So whenever we say that we have a relation R, that means we have a set whose members are ordered pairs, but these ordered pairs will come from A cross B. So sometimes this is called relation from A to B. This is called relation from A to B. So now precisely when we say that relation R is a set of ordered pairs of A cross B, and usually such a relation is called R from A to B. That is, if I just write in a single line, I can say that R is a subset of A cross B. It can be equal also. This is precise meaning of relation from A to B. This much we know from 11th standard. Even R can be empty also. That relation R can be empty. This is called void relation. That means it contains no ordered pair. And this R being subset of A cross B, R can be A cross B itself. That is R equals to A cross B. That is R consisting of all ordered pairs of A cross B. This is sometimes called universal relation. Universal relation. These also you know from 11th standard. Void relation means it consisting of no ordered pairs, and universal relation means it's consisting of all ordered pairs of A cross B. This also you know, if you recall, if one ordered pair A comma B is a member of the relation set R, if and only if we say that A is related to B. We say that A is in fact R related to B. This is a standard symbol. We use this symbol freely here. Remember, whenever one ordered pair A comma B is member of R, relation R, here R does not mean real numbers, remember. Double implies, that is, if you have this must be true. We write A related to B. And conversely, if A related to B, that means the ordered pair A comma B is a member of the relation set R. For example, if I have 1 comma 2 belongs to relation set R, I can write 1 related to 2 that way. If 3 comma 4 is a member of the relation set R, I can write 3 related to 4. Related in the sense that 3 comma 4 is a member of the relation set R. We also know that if a relation R is a subset of A cross A. So instead of two different sets, we are taking same set. Instead of A cross B, we are taking A cross A. Then it is called a relation in a set A, or sometimes it is also called on a set A. Whichever you write, in or both are same things. So what's the difference about this one and the one we defined earlier? The only difference is here both the sets are equal. So when we use the relation in a set, that means it's a subset of A cross A. You are given a single set and you are taking cross product with itself. In earlier case, you used to do with two different sets, A and B. A cross B, here A cross A. Okay. So if I take a simple example, for example, here, let's take A equals to, I'll take randomly one set, 1, 2. Then, A cross A will have 4 ordered pairs. There are 4 ordered pairs in this. 4 ordered pairs. Now, I want to write one relation. So, a relation means any relation. A relation R in A. What's the meaning of this? That means you are writing subset of A cross A. In A as R equals to, now A cross A 4 ordered pairs. I'll just take randomly, for example, 1, 1, 1, 2, and let's take 2, 1. I've taken 3 ordered pairs out of 4. So this R is a subset of A cross A. So this become relation in A. So it consisting of ordered pairs. This is one example. I can take one more relation. Let me call, for example, relation S, which I can take just 2, 2. This is also subset of A cross A. Right? Relation means you are taking ordered pairs from A cross A, remember, because it's a relation in A. Now one more, if I want, I can take T equals to, I can take just this much, 1, 1 and 2, 2. This is also a relation in A. That means it is a subset of A cross A. Here it is a subset of A cross A, remember. I've just taken 3 examples to give a relation from relation R in A, remember. So one is this is relation R in A, this is relation S in A, this is relation T in A, remember. You can find many more. This is just for your information. So for example, relation R, you can say that here 1 related to 1, 1 related to 2, 2 related to 1, because 2, but 2 is not related to 2 in this relation R. Second one, you can say that 2 related to 2, here relation is S, so 2 related to 2, 1, 2 is not in this, so we write 1 is not related to 2, 2, 1 is also not in this, so you can write 2 is not related to 1, and so on. In third example, 1 related to 1 with respect to relation T, so 1 related to 1, 2 related to 2, 1, 2 is not there, so you can say that 1 is not related to 2, and so on. This is just to clarify the concept of symbol over this A related to B symbol, this much only. And these are just simple illustrations to understand what we mean by relation in A. When we say that, we emphasize much on this in this chapter. Relation in A means this is a subset of A cross A, remember. That is second thing. One more thing, number of relations, which also you know from 11th standard. Number of relations in A. So again, total number of relations equals to, now you know a relation is a subset of A cross A. So total number of relations means total subsets of A cross A. Total subsets of A cross A. Now you know from set theory how do you find the total subsets? That is 2 raised to number of elements in A cross A. You can write A cross B also, or if it is a relation from A to B, for example, you can write 2 raised to number of elements in A cross B also. If you have relation from A to B, for example. So this also we know from 11th standard. Total number of relations, it is same as the total number of subsets of A cross A. Now you know from set theory how to find the total number of subsets, that is 2 raised to number of elements in A cross A. You are finding subsets of A cross A, remember, not the subset of A. That's why we are writing 2 raised to number of elements in A cross A. That you know. And that is further, if you want, you can write 2 raised to n of A into n of A. That also you know from set theory. 2 raised to n of A into n of A. Suppose A has 3 members, then 3 into 3, 2 raised to 9. And suppose here A has 2 members and B has 3 members, then there's 2 raised to number of elements in A into number of elements in B. This is from set theory as well as 11th standard, you know. 2 raised to, remember. This much we know from 11th standard here. So let's take an example. Suppose one set A has 3 members, the other set B has 2 members. Then A cross B, you know, it would have 6 members. 2 into 3, which you know, 2 into 3, it would have 6 ordered pairs. So therefore, total number of relations equals to 2 raised to number of elements in A cross B, which is 2 raised to 6, which is, you know, big number 64. Now total number of relations from, of course, from A to B here, remember, from A to B, because this will be all subsets of A cross B. Relations means subsets of A cross B. Now A cross B would have how many ordered pairs? 3 into 2, so 6 ordered pairs. So if you form different list of relations, it will be 2 raised to 6. One more, suppose if I take one example here, let's take A equals to set consisting of A, B, C, 3 members. Then A cross A would have, you know, 3 into 3, 9 ordered pairs. So here total number of relations in A. Now when I say the total number of relations in A, it means subsets of A cross A, remember, subsets of A cross A. It will be 2 raised to number of elements in A cross A. So it will be 2 raised to, remember, 3 into 3, which is 9, which is again a big number. It's difficult to list all, but we have this many subsets of A cross A, remember. So that is one number of relations. So now next, this is actual beginning of this chapter. That's about types of relations. So we start with a relation. A relation R in a set A. Now when I say that a relation R in a set A, it means R is a subset of A cross A. That is just for information. So this is a set consisting of ordered pairs of A cross A, remember. This is a set whose members are from A cross A, remember. So a relation R in a set A is called, first one, reflexive, is called reflexive. A relation R in a set A is called reflexive if A comma A is a member of the relation set R. That is, A related to A for all small a from the set A. That means for every member of the set, A comma A must be present in the relation set R. Suppose A has 10 members, 1, 2, 3, 4 up to 10. Then 1 comma 1 should be there, 2 comma 2 should be there, 3 comma 3 should be there, 4 comma 4 should be there, and so on till 10 comma 10. It may or may not have other members, remember, but at least this much should be present for every member of the set. A comma A must be present in the relation set. That means here we say that every member is related to itself. Every member of the set is related to itself. Suppose set has 3 members. Here A has only 3 members, for example 1, 2, 3. Then 1, 1 should be there, 2, 2 should be there, and 3, 3, 3 should be there. Then such a relation is called reflexive. Then second, I'll take example once I finish all types. The second one, that is symmetric. A relation R in a set A is called symmetric. A relation R in a set A is called symmetric if whenever A comma B is member of the relation set R, then implies B comma A must be member of the relation set R. That means reverse ordered pair should be present. A comma B is a member of R, then B comma A should be member of R for all AB, remember. That A and B of course comes from the set A. All members comes from the set A only. I repeat this, what it says. Whenever one ordered pair is present, then its reverse must be present. Then it is called symmetric relation. If you have 1 comma 2, then 2 comma 1 should be there. If you have 3 comma 4, then 4 comma 3 should be there. If you have 5 comma 6, then 6 comma 5 should be there. That is, whenever A related to B, it implies B must be related to A. It means whenever A related to B, then B must be related to A. Such a relation is called symmetric relation. First, let's recall reflexive. Reflexive means for every member of the set, A comma A must be member of the relation set R. That means A related to A. What is this? This says that whenever one ordered pair is present, then its reverse must be present. For example, if you have 3 comma 4, then 4 comma 3 should be there. And if it is true for all ordered pairs, then it is called symmetric relation. So now third type is transitive relation. So it says that whenever A comma B is a member of the relation set R, you take one more ordered pair having this common element, that is B comma C also a member of relation set R. Remember, you have not taken randomly 2 ordered pairs. You have chosen 2 ordered pairs having this common member, like 1 comma 2 and 2 comma 3, that way. Then it implies, so this much should be there. Then you check whether A comma C is a member of the relation set or not. If it is, then it is called transitive relation. I repeat, what is this? A relation is said to be transitive if whenever A comma B is a member of the relation set R, that is A related to B, then again we start with B related to C. It implies you drop the common one, then A related to C. If this is true for every A, B, C in the set A, then it is known as transitive relation. Again, what is this? This definition says that you must have such 2 ordered pairs. Which type of the ordered pairs? Having this common element, like 1 comma 2, 2 comma 4, then 1 comma 4 should be there. If it is true, then for all members of the set A, then it is called transitive relation. Again I repeat, A comma B and B comma C both are members of the relation set R. Then you check whether this is there or not. If A comma C is not the member of relation R, then it's not transitive. This should be present, remember, then and then you can check for the third one. So these are the three properties. The one we did, that is reflexive relation here. So a relation R in a set A is called reflexive if A comma A is a member of the relation set R for every member of the set. It is called symmetric if whenever ordered pair is present, then its reverse must be present, then it is called symmetric. So here you had one ordered pair, now reverse should be present. Now here you have two ordered pairs, but with this condition, B should be common. Then A comma C should be member of the relation set R. If it is true, then such a relation is called transitive relation. So I will take a simple example here just to understand this. For example, let's take one set A equals to, I'll take one set A equals to, for example, 1, 2, 3, 4. So in a set you have 4 members. This is given to you. Define a relation. This is given to you. Define a relation in A. Now when we say that we are defining a relation in a set A, means relation will be relation, let me call R. Relation R will be subset of which set? A cross A, remember. Now A cross A would have 16 ordered pairs. Out of 16 I am taking some ordered pairs. R in A as R equals to, I am taking in this way. Suppose I have this 1 comma 1. Let me take 1 comma 2. Here let me take 2 comma 1, 2 comma 2, 2 comma 3, 3 comma 2, 3 comma 3 and 4 comma 4. This is given to you. You are not going to decide. Remember, this is a subset of A cross A. So it's a relation in A. This is given to you. Out of 16 I have chosen how many? 3 plus 2, 5 plus 3, just 8 ordered pairs. This you are not going to decide. This is given to you. The question is R reflexive? That's the question. Is this reflexive relation? Is this symmetric relation? This is the question. Is this transitive relation? That is the third question. Okay. Is this relation R? Is R reflexive? That's the first question. Is R symmetric? That's the second question. Is R transitive? That's the third question. So in the solution, now recall reflexive property. What is the reflexive property? For every member of the set, that element must be related to itself. So your first member is 1. 1 is a member of A. Here 1 related to 1. Second member 2. Do you have 2 related to 2? Yes. 2 related to 2. That means 2 comma 2 is in R. Third member 3. Do you have 3 related to 3? Yes. So here 3 related to 3. 4 related to 4 is also there. 4 related to 4. So therefore, you can say that R is reflexive. In case if I drop this, for example, suppose I have dropped this 4 from this 4 comma 4, sorry, then this will not be reflexive because 1 comma 1 is there, 2 comma 2 is there, 3 comma 3 is there. But if I drop this, then it will not be reflexive. For, I repeat and I emphasize again, for every member of the domain or the set, each member must be related to itself. So 1 comma 1 should be there, 2 comma 2 should be there, 3 comma 3 should be there, and 4 comma 4 should be there. Then it is called reflexive. If I drop one member, suppose I have written up to this, so now 4 comma 4 is not there, so it is not reflexive. We go to second property now, here, which is symmetric. Now what's the symmetric property? Reverse should be present. So we start with 1. Here 1 comma 1 is a member of the relation set R. If you reverse it, you will get the itself, which is also in R. You can write like this: 1 related to 1 implies 1 related to 1. Its reverse is itself, and which is also in R. Now go to 1 comma 1 comma second ordered pair. 1 comma 2 is a member of the relation set R. Now reverse it. Ask yourself whether 2 comma 1 is a member of the relation set or not. It is there. I've written in such a way 1 comma 2 and 2 comma 1 both are present. If you want, you can write like this also: 1 related to 2 implies 2 related to 1. Go to next 2 comma 1. If I take 2 related to 1 here, now 2 related to 1, check the reverse. What's the reverse? 1 related to 2, that is 1 comma 2, which is also there. Then you can write like this also. Remember, 1 comma 2 comma 1 is a member of the relation set R. Its reverse 1 comma 2 is also member of the relation set R. You can use this symbol or this symbol freely, not both. Remember, I'm just showing for your information. Then go to next 2 comma 2. You reverse it. 2 comma 2 is a member of the relation set R. You reverse it, you will get itself. Then go to 2 comma 3. What's the reverse of this? 3 comma 2, which is here. Go to 3 comma 2. What's the reverse of that? 2 comma 3, which is present. Come to this 3 comma 3. Reverse is itself. 4 comma 4, reverse is itself. So for every ordered pair, reverse is present. So you can say that for every A comma B belongs to R, its reverse B comma A is also in R, remember. So therefore this relation is symmetric. I hope now this is clear to you. Now third property of the same relation. For example, here 1 related to 1 comma 1 is a member of the relation set R. Now you find all ordered pairs having 1 at the first place. So you can take 1 comma 2, which is also in R. Now it implies check whether 1 comma 2 is in R or not. What about 1 comma 2, which is second itself, which is in R? Now, do you have any ordered pair having 1 at the first place? No. So here you are through. Now let's go to this 1 comma 2. I'm checking for second one. 1 comma 2 belongs to R. It's a member of the relation. Now you find all ordered pairs having 2 at the first place. So I can take this. So 2 comma 1 is a member of the relation set R. Now you check whether 1 comma 1 is a member of the relation set or not. You drop this common one, check for 1 1. Is it there in R? Yes. Okay. Now here you had 1 comma 2. I've chosen 2 comma 1. Do you have any other ordered pair having 2 at the first place? Yes. One more, you can take these also. So 1 comma 2 is in R. Then you can take 2 comma 2, which is also in R. Now you check, you drop this common one, 1 comma 2. Is it there in R? 1 comma 2 is this. It is also there in R. So in this case also you are through. Any other ordered pair having 2 at the first place? Yes, one more here. So 1 comma 2 is in R. And then 2 comma 3 is also in R. 1 comma 2 and then 2 comma 3. So if you go for common drop, if I drop the common one, you have 1 comma 3. Is it there in the relation set? If you notice, 1 comma 3 is not there in the relation set. So now you can stop and you can say that R is not transitive. R is not transitive. No need to check further. Now just by observation, if you find such 2 ordered pairs which are present in the relation but third one is not, so directly you can write it is not transitive. No need to show for this. Usually to check the relation transitive or not, it's not easy task. It becomes tedious also sometimes. One more ordered pair I can find. You can see 3 comma 2 is present. 3 is related to 2. I can take 2 comma 3, which is also in R. But in that case 3 comma 3 is there. Here it is there, remember. So no need to check for this. It is there, but if I take even this 3 comma 2 is in R, and if I take 2 comma 1, that is also in R. But if I drop this common one, 3 comma 1, probably this is also not there in the relation. So here also you can say that it is not transitive, right? So this, from this or this one, any one will suffice that this is not transitive. This is one more illustration I have given. Here you can conclude that this is not transitive. Now, just by observation, if you notice the first case where it is this condition is true, that is third ordered pair is not a member of the relation set, then directly you can say that it is not transitive. No need to show for this. Remember, transitive means for all ordered pairs, third ordered pair should be present. Here you have an example for which third ordered pair is not present, therefore it is not transitive. So the above example relation is reflexive, symmetric, but not transitive. One more, I'll take example number 2. Let's take A equals 2. For example, I'll take 2, 3, 4. And I'll define a relation like this. Define a relation R as R equals to x comma y such that x less than y, and where obviously x and y both are members of A. Such things you did in 11th if you recall. So first we write the members of the relation set R here. How do we write the members of the relation set R? You know A cross A would have 9 ordered pairs. So you find all ordered pair for which this condition is true. So for example, if I take 2, 2 you cannot take because 2 is not less than 3. So 2, 3, then 2, 4. Then go to next. Can I write 3, 2? No. 3, 3? No. So 3, 4. Then next, if I go for next one, can I write 4, 2? No. 4, 3? No. 4, 4? No. So only you have this many ordered pairs. So here A cross A has total 9 ordered pairs. Out of 9, only 3 ordered pairs satisfy this condition. This is given to you, remember. You are not going to choose this. Now the question is this reflexive, symmetric, and transitive? That's the question. So the first one, it's very obvious that it's not reflexive. Why it's not reflexive? What's the definition of reflexive? For each member of the set, 2, 2 should be there, 3, 3 should be there, and 4, 4 should be there. But here 2, 2 is not there, 3, 3 even is not there. So that's why. So 2, 2 is not a member of the relation set R, and so on. Not reflexive. What do you think about symmetric? Symmetric means reverse ordered pair should be present. So here 2, 3 is in R. Do you have reverse? No. 3, 2 is not a member of the relation set R, you can see. So not symmetric. Let's go to third one. Third property, transitivity. So for example, I'll take 2, 3. Now find all ordered pairs having 3 at the first place, that is this. So here 2, 3 is a member of relation set R. Now you take ordered pair having 3 at the first place. So I can take 3, 4 is in R. But 2, 4, what about 2, 4? That is there. It's there in R. So it implies this. Now go to this. 2, 4 is there. Go to this. 2, 4. Do you have any ordered pairs having 4 at the first place? No. So no need to check for this. Go for this. 3, 4. Do you have any ordered pairs having 4 at the first place? No. So here there is only one ordered pair for which this condition is true. Therefore it is a transitive relation. Transitive relation. Reason is this. I repeat. Why it is transitive? Because see, if I take first ordered pair 2, 3, then find all ordered pairs having 3 at the first place. So that is this one. So 2 comma 3, 3 comma 4. Then 2 comma 4 should be there, which is there. Go to next ordered pair, 2 comma 4. Now you have to find all ordered pairs having 4 at the first place. We don't have any ordered pair having 4 at the first place. So for this we cannot check. Go to next 3 comma 4. Do you have any ordered pair having 4 at the first place? No. So you cannot check for this also. So therefore this turns out to be a transitive relation. Next we go for equivalence relation. So a relation R in a set A is called equivalence if R is reflexive, symmetric and transitive. If relations satisfy all the three properties which were discussed, reflexive, symmetric and transitive. If a relation R satisfy all the three properties, reflexive, symmetric and transitive, then it is known as equivalence relation. For example, you take this, let's take A equals to, I'll take 1, 2, 3, 3 members. Define a relation R in A as R equals to, I'll take like this, 1, 1, then for example 1, 2, 1, 3, then 2, 1, 2, 2, 2, 3, then 3, 1, 3, 2, 3, 3. You must have realized what I did here. Suppose I've taken this way. This is a relation in A. It is a subset of A cross A. In fact, I've chosen A cross A itself. Now clearly you can see, I leave it for you, it is reflexive. Why? 1, 1 is present, 2, 2 is present and 3, 3 is present. So it's reflexive. It's reflexive. What's the reason? 1 related to 1, 2 related to 2 and 3 related to 3. Right? 1 comma 1 is present, 2 comma 2 is present and 3 comma 3 is present. Symmetric, let's check the symmetric property. 1, 1 reverses itself. 1 comma 2 is there, 2 comma 1 is there. 1 comma 3 is there, 3 comma 1 is there. 2 comma 1, 1 comma 2. 2 comma 2 reverses itself. 2 comma 3, 3 comma 2. 3 comma 1, 1 comma 3. 3 comma 2, 2 comma 3. 3 comma 3 reverses itself. So it's symmetric. Reason, you can verify for every AB in the relation set R, it implies its reverse is also present in R. So it is symmetric. Third one, transitive property. What about transitive? Let's see this. You take any ordered pair randomly. Suppose I have taken 1 comma 1. Now you get all ordered pairs having 1 at the first place. Suppose I have taken 1, 2, which is also there in the relation set R. Drop the common one. So 1, 2 is in R. Then you can take 1, 3 also. 1, 1, 1, 3. Then 1, 3 is present. Now you go to this 1, 2. Now you get all ordered pairs having 2 at the first place. So for example, I have taken 1, 2 and 2, 1. Both are present in R. Drop the common one. So you are left with 1, 1. Is it there in R? Yes. Similarly, you can take 2, 2 also. 1, 2 here. 1, 2 and 2, 2. So you hide the common one. So you are left with 1, 2, which is itself. Then you can take these two also. 1, 2 and 1, 3. So 1, 3 should be there, which is this one. Similarly, you can try for all other elements also. Whenever two members are present, suppose I have taken this 2. 3, 1 and 1, 1, 3. So if I hide a common one, 3, 3 is also present. 3, 2 and I have taken 2, 3. So 3, 3 is also present. So for every AB in R, BC is also in R, then AC is also in R. So this is transitive also, transitive, symmetric and reflexive. Therefore here R is an equivalence relation. R is an equivalence relation. It satisfies all the three properties of the relation. So here relation is equivalence.